Okay, so homework 1 was due last Friday. Most people have turned it in, but if you haven't, please try to get it in soon. Like I said, I'll take it up to this Friday without penalty. I mean, if there's reasons you need to turn it in after that, I'll be reasonable, but we're hoping to try to get it graded sometime this weekend, and we kind of need all of them turned in order to do that. And I'm going to try to put together homework 2 and put it on Sakai tonight, so just to give everyone the heads up. At any rate, today's lecture and the next couple lectures, unfortunately, are going to be a little bit on the theoretical side. I feel bad torturing you with this, especially given the composition of this class, but the normal distribution and the central limit theorem is just kind of such a fundamental part of all statistical inference, and it's used so frequently that it's important to at least understand the basics behind it. Don't worry too much about the math and the nitty-gritty. This isn't something that I'm going to be testing you on or anything, or at least the math and theory behind it, but the important thing is just the general concepts of when you can use the central limit theorem and why it's important for statistical inference, and we'll be going over that over the course of most of the rest of this week. So at any rate, before we get into the central limit theorem at all, we need to talk about this idea of random variables, which is basically the simplest definition of it is it's a variable that takes numerical values depending on the outcome of some chance operation. Formally, a random variable is a function between an outcome space to a continuous number, but yeah, I really don't want to torture you with all those hairy details. Oh, the simpler explanation of a random variable, say that you roll a fair die, you count the number of spots. Easy enough. You can talk about probabilities of random variables. The probability that x equals 4 is 1/6. The probability, and that is a typo, 2 less than or equal to x less than or equal to 6. I think that should be, I don't know if that's a typo or if something got messed up when I converted this from OpenOffice to PowerPoint. That should be 2 strictly less than x, strictly less than 6, and otherwise equal to 3, 4, 5, which equal to 1/2. I'll see whether that's a problem with my slides or when I converted this. But another example, if you assume the height of men in the U.S. population has a certain distribution, then you can say that the probability that someone has a height between 65.2 inches and 70.4 inches is about 0.46. And you can classify random variables as either discrete or continuous. A discrete random variable is a variable that can only assume a finite or countable number of outcomes. That number of spots on a die, there's 6 possibilities, which is a discrete number. Or you flip a coin 5 times, count the number of heads, that's going to be a discrete number between 0 and 5. And it would still be considered a discrete random variable if you counted the number of tosses until you get a head. That's what I mean when I say a countable number of outcomes, that basically there's an infinite number of outcomes. Theoretically, it can be 0, 1, 2, 3, 4, 5, up to 10 trillion for that matter. But you can basically put the number of outcomes in a one-to-one correspondence with 1, 2, 3, 4, 5 sort of thing. It's not like a continuous range like height could be. If you didn't understand what I just said, don't worry about it because it's probably shouldn't have even brought it up anyway. A continuous random variable, on the other hand, is something that can assume a continuous range of values. That, like height, in theory, if we could measure it with perfect accuracy, could be 65.43729116, etc., inches. So it's a continuum rather than list of numbers, or weight, or gene expression level, anything like that would be considered a continuous random variable. And for a continuous random variable, the probability of getting any one outcome is 0 for any value of the outcome. I mean, in theory, if you could measure height with perfect accuracy, then since there's an infinite number of possible values, the probability of drawing any one value is 0. It's just so small, it's completely negligible. So all you can talk about is probability of ranges. You can't find the probability that someone's exactly 66.2 inches tall, because if you could measure their height with perfect accuracy, they'll always be a little more, a little less than that. But it does make sense to talk about the probability that someone is between 65 and 68 inches tall. And random variables, you can define what's called the density function, which is basically the probability of observing a particular outcome. Here I've plotted the density function for, I think, the number of heads you observe when you toss some type of weighted coin. In this case, the most likely scenario is about 1 or 2 heads, and the probability steadily decreases for more heads than that. Our continuous density function would look something like this, and I guess that's something I didn't mention on the earlier slide, that for this discrete density function, if you want to define the probability that x is equal to 0 or 1, you would just basically count the height of each bar and sum them together. For a continuous density function, you calculate probability that x within a certain range by calculating the area under the curve for a particular range of values. And I'll give some examples of that later on today. And for a discrete random variable, all the probabilities must sum to 1, since there's just a finite number of possible outcomes, or at least a countable number, a number that you can enumerate. You add up all the probabilities, they have to sum to 1. For a continuous random variable, the area under the entire density function has to be 1. In other words, if for something like height, the probability that somebody's height is between minus infinity and infinity has to be 1. Something like that. And you can define this concept called expected value of a random variable. It's essentially the mean of a random variable. The way you calculate it is, if, at least for a discrete random variable where you have a finite number of outcomes, you take the value of the first possible value of the random variable times the probability of that outcome, plus the second possible outcome times the probability of that outcome, and so on up to the last outcome. If all outcomes are equally likely, then each one of these probabilities would be 1 over k, and the expected value would just be the sum of all possible outcomes divided by the number of outcomes, exactly the same as the mean. The expected value is just a little bit more general in that we don't necessarily assume that all outcomes are equally likely, so you sort of take a weighted mean, that each value is weighted by the probability of observing that particular value. So let's use our dice example again. You roll 1 fair die and count the number of spots on the die. Well, in this case, all outcomes are equally likely, so we essentially take the sum of the numbers 1 through 6. Divided by 6, it's equal to 3.5, as we expect it would be. Or another possibility, and that's unfortunate, it looks like when I put these slides together, I create them in OpenOffice, then convert them to PowerPoint, then open them in Keynote, because only Keynote will record lectures under the Mac, and sometimes stuff gets lost in the conversion, so I apologize for that. If you open the PDF that's on Sakai, this should look a little better. But if you could actually read this, what it's supposed to say is that you're running some sort of health clinic and you have preschool children that come into your clinic periodically, occasionally with ear infections, and you keep track of how many ear infections each child has per year in your clinic. And you find that 58% of the children in your clinic have no ear infections, 27% have 1, 9% have 2, 5% have 3, and 1% have 4. Oh, the expected number of ear infections would be 0 times 0.58 plus 1 times 0.27 plus 2 times 0.09 and so on. End up with an expected value of 0.6 ear infections per child. The variance of a random variable is closely related to the idea of variance and standard deviation that we talked about before, is that it's just basically the square of the standard deviation, or more to the point, you calculate it like we calculated variance before, that you take each value of the random variable minus its expected value or minus its mean, square it, times the probability of observing that particular value. Then you sum all those up. Once again, if all the probabilities are equal, then you take the value minus the mean squared divided by the number of observations, which is the same or virtually the same as the formula for the variance or the square of the standard deviation. So in the dice example, to calculate the variance, and when you roll one fair die, you go 1 minus the mean, i.e. 3.5 squared times 1/6 plus 2 minus 3.5 squared times 0.6, 3 minus 3.5 squared times, or divided by 6, etc., etc. Sum all that up, you end up with the variance of 2.92. And the ear infections example with the table that is unreadable in Keynote would be, recall the expected value is 0.64, so we go 0 minus 0.64 squared times 0.58 plus 1 minus 0.64 squared times 0.27. Again, add all that up, we get 0.83. If I ask you to do anything at all like this in this class, it'll be like 1 or 2 homework problems. This isn't really a major thing that you'll be doing on a regular basis, but it's good to be familiar with the concept because you'll be using the concepts of mean and standard deviation throughout this course and throughout your life as long as you're doing science that requires statistics. So, to find the expected value and variances of continuous random variables, the short answer is that you need to do some calculus operations that basically you take the integral of x times the density function. Definitely not going to ask you to do that in this class, just thought I'd mention it in case you ever encountered that for some bizarre reason. Okay. Couple other things to know about means and standard deviations that come in handy on occasion if you're ever converting variables between one set of units to another is the most common situation where you would use this. That basically if x is a random variable and A and B are constants, then the expected value of a plus bx is just equal to a plus b times the expected value of x. In other words, if you know if you know the expected value of a given random variable x and you add something to it or you multiply it by something, say you have data collected in Fahrenheit, you need to convert it to Celsius, for instance, you don't need to recompute the mean after performing the conversion. If you know the mean in one set of units, you can just convert your numbers and automatically convert the mean as well. Likewise, if you have two random variables and you want to find the expected value of the sum of the two random variables, that's just the sum of the expected value of each random variable individually. So let's say that you're running some type of clinic, you administer X vaccines per day, Y is the total cost of the vaccines. Say that you have to pay the people who work in your clinic and your rent a total of $250 per day, and the cost of each vaccine is $3. Let's say we know from past experience that usually the expected value of the number of people who come into the clinic per day is 120. Then the expected cost would just be 250 plus 3 times 120, so most days it costs you $610 to keep your clinic open. And similar rules work for the variance, that if you have a random variable and two constants, you want to, and you have an A plus BX type of transformation, you're converting to Celsius or Fahrenheit again, for instance, then the A makes no difference whatsoever, and the B, you just have to square it before you multiply it by the variance. It ends up being B squared times the variance of X. And the rule about variance of X plus Y equals variance of X plus variance Y, that works only if X and Y are independent. That is, if knowing the value of X doesn't give you any information about the value of Y. If they're dependent, then all bets are off. There's actually a formula for the case where they're dependent, but I won't ask you to mess with that, I don't think. So once again, let's take our vaccine example. Let's suppose the variance in the number of people who come in per day is 225. Then the variance of the cost per day would be 3 squared times 225. Recall the formula from the previous slide. The 250 doesn't matter. And then the thing that you multiply x by, in this case 3, you square that. So you end up with 3 squared, i.e. 9 times 225. And if you wanted to find the standard deviation, you can take the square root of that, which works out to be 45 in this case. And one important consequence of this formula is, if you do some simple math that I won't bother to write out, the expected value of the mean of a bunch of variables, say for instance that you, instead of rolling 1 die, you roll 10 dice and then take the mean of the 10 die rolls, the expected value of this mean is the same as the expected value of 1 die roll. That is, if you take the mean over 10 die rolls, the expected value is 3.5, just like it was for a single die roll. However, the variance of the mean turns out to be the variance of a single observation divided by n. So the implication is that if you take a mean of if you measure the same quantity a bunch of different times and take the mean of that, the expected value of the mean is the same as the expected value of an individual observation, but the variance gets smaller, and that makes intuitive sense. that if you roll one die, you could get a 1, you could get a 6, whatever. But if you roll 10 dice, it's really unlikely that you're going to roll 10 sixes in a row, but that's the only way that you could get a 6. Most likely, it'll be a number larger than 1 or smaller than 6, hence the variance gets smaller. And this leads to an important mathematical property called the law of large numbers, which says you select a bunch of independent observations from any population. As the number of observations gets larger, the sample mean will approach the population mean. In the dice example, if you roll enough dice, the mean value of the dice will get closer and closer to 3.5. Or if you survey a large number of people from the US population, take their average height, once you survey a sufficiently large number of people, their average height will be very close to the average height of the overall population. This graph down here illustrates a simple example of this, where they basically did a computer simulation of flipping a coin a bunch of times and keeping track, and obviously the probability of heads is 50%, so for the long run you would expect to observe approximately 50% heads. This graph down here shows the number of heads that were actually observed either in excess or below 50%. You can see for a small number of tosses it was a long ways away from 50% for a while, but as the number of tosses increases, pretty soon the total number of heads becomes very close to 50%. The law of large numbers says if you repeat measurements from the same population enough times and take the average, it will get very close to the population average eventually. And now we're going to briefly describe a special type of random variable, namely normal random variables that come from the normal distribution. Over the course of the rest of this week, I'll explain to you why the normal distribution is so important and why we talk about it so much. But basically, normal distributions they're an example of the famous bell curve. They're symmetric, bell-shaped, and the shape of the normal distribution is completely defined by their mean, mu, and their standard deviation, which is usually denoted by sigma. This is the formula for the density of a normal distribution that you will never use in this class, but I just wrote it there so you would know what it is if the subject ever came up. And this slide here shows a couple examples of a normal distribution that basically the mean of the normal distribution just tells you what number it's centered around. If the mean is 0, then the bell curve is centered around 0. If the mean is 150, as it is in this case, it's centered around 150. The highest point of the bell curve is always at the mean. And the standard deviation sigma determines the shape of the bell curve. That if sigma is small, that implies there's not much variation in the data, so almost all of the data is concentrated very close to the mean, as you can see here. On the other hand, if sigma is larger, then the bell curve is flatter, the data is much more spread out. So leads to a flatter curve because there's a greater probability that the data is further away from the mean. So a possible example of normally distributed data was an example I found in a book somewhere on the lengths of a particular type of fish. There was a researcher who had determined that this particular population of herring, the lengths of an individual fish follow a normal distribution with mean 54 millimeters and standard deviation 4.5 millimeters. And using known properties of the normal distribution, you can calculate probability that the data that you will observe will fall within a specific range. For example, let's say we wanted to determine what proportion of the fish are less than 60 millimeters. So this graph here shows the normal density function in this case that, remember, the mean is about 54. I can't even remember what I said in the previous slide. Standard deviation is about 4.5. We want to find the probability that a given fish has a length of 60 millimeters or less. In other words, we want to find the area under the bell curve that's shaded in red here. Recall that for a continuous density function to find probabilities, you just calculate the area under this bell curve. In this case, we want the full area that's less than 60. In other words, the part that's shaded in red. And to actually calculate that area, you have to do a bunch of really horrendous calculus stuff that, but luckily we don't need to do that anymore because R will do it for us. There's this command in R called pnorm, which takes 3 parameters. Basically, pnorm, the second and third parameters, the second parameter is the mean of the normal distribution that you're looking at. The third parameter is the standard deviation. So in this case, the fish have a mean of mean length of 54 millimeters, standard deviation of 4.5 millimeters. And the first value for pnorm is the number that you want to find the area less than. So this says, given a normal distribution with mean 54 and standard deviation 4.5, find the probability that a given observation, in this case a given fish, has length 60 or less. And the probability in this case is about 91%. So just went over most of this already. Pnorm command in R. In general, if you say pnorm q of mean, comma, sd, that computes the probability that a normally distributed random variable with mean, and standard deviation sd is less than q. So pnorm 60, 54, 4.5 computes the probability that a normally distributed random variable with mean 54 and standard deviation 4.5 is less than 60. Blah. So that was easy enough. In some problems, it's not necessarily going to be that straightforward. Let's say that we want to find the proportion of fish that are more than 51 millimeters long. In other words, we want to find this area under the bell curve. Well, the pnorm command in R always finds the area less than a given number. In this case, we want the area greater than the given number, so we can't just apply pnorm directly. Luckily, this is easy enough to work around that we know the area under the entire curve is 1, so the area of the red part of the curve has to be equal to 1 minus the area under the white part of the curve, and to find the area under the white part of the curve, we can just use pnorm and plug in 51. So the R commands are right here. As I said before, we just go 1 minus pnorm, 51, 54, 4.5. We end up with a probability of about 75%. And we can make this even a bit more complicated if we want. Let's say that we want to find what percentage of the fish are between 51 millimeters and 60 millimeters. In this case, the red area of the curve doesn't go all the way out to the end on either one side or the other. We want to find the part in the middle. So how can we do that? Well, in this case, we just have to do some subtraction. To find the probability that it's less than 60, we can do pnorm 60, comma, mean SD, find the area to the left of 60, and then just subtract off the area that's to the left of 51. So in other words, the R commands would be pnorm 60, 54, 4.5 minus pnorm 51, 54, 4.5. End up with a probability of about 66% that the length of a given fish is between 60 millimeters and 51 millimeters. And let's say that you want to do this in reverse. Let's say that we want that, let's say, what's the 70% quantile of the fish length distribution? In other words, what length of fish is, or 70% of the fish are less than what length? In the days before R and other statistical packages were invented, calculating something like this was a major headache, but with R, luckily, it's trivially easy. There's this command qnorm in R, which stands for quantile of the normal distribution. In this case, rather than giving it a value of x, a given data value, you give it the quantile that you want. In this case, we want the 70% quantile, so we say qnorm 0.7, 54, 4.5. We end up with a value of about 56.36. In other words, 70% of the fish will be of length 56.36 or less. And one situation where doing this sort of thing would be useful, let's say that you want to find a 95% confidence interval for the size of the fish. In other words, you want to choose an upper and lower bound such that 95% of the fish will be within these two bounds. Oh, in other words, I mean, there's various ways you can do it, but the simplest way is if you take the 2.5% quantile and the 97.5% quantile of this distribution, then 95% of the data should be between these two quantiles. And calculating these quantiles is very easy using R. Once again, you can just say qnorm 0.025, 54, 4.5, qnorm 97.5, 54, 4.5, and we see that 95% of the fish in this population should have a length of between 45.2 millimeters and 62.8 millimeters. This was kind of a simple toy example, but this is essentially what you do when you calculate confidence intervals for any type of statistical analysis, that you calculate like the mean expression level of a particular gene in a genetic experiment. You calculate like the mean amount of urea excreted in an experiment on liver cells that I'll show you in a couple days. Whatever the case may be, if you want to report these results in a journal, it's pretty much mandatory that you report a 95% confidence interval first mean and say, okay, here's the mean that we observe, but we're 95% confident the true mean is within this specified interval. To calculate it, you will essentially do this. I'll show you a bit more details about how this is done over the course of the next week or two. And I'll note in passing that whenever you have a number x from pretty much any distribution whatsoever, you can convert the data to a standardized value, more commonly called a z-score, by taking each given data point, subtract the mean, and divide by the standard deviation. Basically, the z-score represents the number of standard deviations away from the mean that a particular data point is, and also the direction. If it's above the mean, the z-score will be positive. If it's below the mean, the z-score will be negative. And I mean, so for example, in R, as you can see, if we look at the herring example, we can say pnorm 60, 54, 4.5 would get a probability of about 91%, but we could also standardize it. Take 60 minus 54, subtract the mean 54 divided by the standard deviation of 4.5. That should be normal distribution with mean 0 and standard deviation 1. So rather than giving 54 4.5, we say pnorm 0, 1. We get the same probability. So what's the point of that exercise, you might ask? Well, nowadays, not much. Once upon a time, hesitate to admit this, it makes me seem really old, but when I took elementary statistics class, we didn't have software available to compute this sort of things. We had to look up these normal tables at the back of the book. We obviously couldn't compute normal tables for every possible mean and standard deviation out there, so they only computed the table for the normal distribution with mean 0 and standard deviation 1. So whenever you wanted to calculate anything using the normal distribution, you had to subtract the mean, divide by the standard deviation, go look it up in your table at the back of your book. Nowadays, we can just specify the mean and standard deviation in R and calculate it that way, so we don't need to convert everything to z-scores anymore. Occasionally, you'll still use them in papers and so forth for other reasons, like, say, for example, you want to compare measurements on different scales that, one example in the study I'm working on right now, it's basically study of gender and racial variation in sensitivity to experimental pain, that basically in these experiments, well, quite frankly, we just kind of like poked, stabbed, and burned people and asked them how much it hurt. And we want to know, like, are women more sensitive than men? Are African Americans more sensitive than Caucasians, and so forth? But, like, pressure pain sensitivity is measured basically the amount of force the person can endure in newtons, whereas mechanical pain sensitivity, we ask them to rate their pain on a scale from 0 to 100. Basically, it's complete apples to oranges. We can't compare the numbers from one set of measurements to the numbers to others, so we convert everything to z-scores and just say women are this much more sensitive than men with respect to pressure, and this much more sensitive to men with respect to mechanical, so everything's on the same axis. So these are not completely useless anymore, but we don't use them nearly as much as they were used in the past. So things to remember for today is that random variables will take on numerical values depending on a chance operation, and for a random variable you can compute its expected value and variance. Normal distribution is a special bell-shaped distribution defined by mean and standard deviation. And it looks like the bottom of this slide disappeared when I converted it to Keynote, but says if you know the mean and standard deviation of a normal distribution, we can compute probabilities and confidence intervals and things like that using R. And R commands to remember for today, if you want to find the area or the probability of observing less than Q in a normal distribution with a given mean and standard deviation, you can use pnorm. If you want to do that in reverse, that you want to find the pth quantile of a normal distribution, then you can use this command qnorm, and in principle you can use that to compute confidence intervals and so on. Any questions about anything today? I don't know how I keep giving these lectures faster every single year. They used to fill 50 minutes, now they don't. I don't think anybody's crying too much that we're getting out of class early, so